We'll solve this differential equation by the use of an integrating factor. It's clear to see that we will not be able to separate the variables in this case, so the first thing we'll do is divide throughout by cos x. That will give dy by dx minus 2y tan x equals x divided by cos x. We'll tidy that up just a little and say dy by dx minus 2 tan x times by y equals x divided by cos x. Now we know that the integrating factor is given by e to the integral of p of x dx, and the function p of x is essentially the function in front of y. We must ensure that we include this minus sign too, and so in this particular case our integrating factor will be e to the integral of minus 2 tan x dx. So, tidying up again, the integrating factor will be equal to e. Let's bring that constant to the other side of the integral sign, tan x dx, and that's a fairly straightforward integral now. It's e to the minus 2, and the integral of tan x is the ln of sec x. As we saw in the general case, I don't need to bother with the plus c. That would simply generate another constant, which would become a times by this, and the a's would cancel out. Check back the previous video if you're a little bit unsure why we don't need to use a constant after that integration. Right, well, we can tidy this up further. So the integrating factor is equal to e to the ln, for the sec x I think I'm going to write 1 over cos x, and that can be raised, if we take the minus 2 up as a power as shown, put the e to the ln function there, so that's going to become quite simply the cos squared of x. So we now have our integrating factor. Okay, the next job is to go back to our modified differential equation, the one that started with just dy by dx, and multiply throughout by cos squared x. So if we do that, we will have cos squared x dy by dx minus cos squared x times by 2 tan x times y is equal to cos squared x times x over cos x. Now that's starting to look quite cumbersome, but remember, the whole purpose of the integrating factor is to ensure that the left hand side can be written directly using the product rule. And I'll be honest with you, you don't even need to check that that's the case. It will be the case. So the left hand side can be rewritten as d by dx of cos squared x times y, and that should now be equal to, just tidying up the right hand side, x cos x. You could, if you really wanted to, use the product rule on d by dx of cos squared x times y to check that you do get something that's algebraically equivalent to the line above, but as I say, you don't really need to. We can now integrate both sides with respect to x, so the left hand side will simply give this function, and the right hand side will be the integral of x cos x dx, which we should recognise as a case requiring the use of integration by parts, and so we'll get cos squared x, oops, cos squared x times y is equal to. Okay, let me just scroll this a little. We're going to let u equal x, v dash equal cos x, so u dash is equal to 1 and v is equal to the integral of cos x, which is simply sin x. So we can now say that cos squared x times y is equal to u times v, which is x sin x. Now it will be minus the integral of u dash v, in other words minus the integral of sin x. Well, the integral of sin x is minus cos x, so I get minus cos x, which of course is plus cos x, and this time I will use a constant of integration, of course, plus c. Now that's the answer. We could tidy this up, of course. Okay, so dividing throughout by cos squared x will give y is equal to x sin x over cos squared x plus cos x over cos squared x plus c over cos squared x, and we can write that as y equals x tan x times sec x plus sec x plus c times sec squared x, and that is the general solution to the given differential equation. If we were given boundary conditions, i.e. a value of x and y, we'd be able to find the constant c, and then we'd be able to give a particular solution.